Tiki 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 mate tiki taka. Tiki 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 tiki.
Today we're going to find the equations of motion for this two-spring system. So we have two springs, each with spring constant k. x2 is the distance of equilibrium from this spring, x1 is the distance of equilibrium from this spring, and we have two masses attached to each spring. Okay, so let's start with the kinetic energy. So the kinetic energy is also equal to T, which is equal to 1/2 mv1 squared plus 1/2 mv2 squared, which in dot notation is equal to 1/2 mx dot 1 squared plus 1/2 mx dot 2 squared. So that's our equation for our kinetic energy. Now we're going to find our potential energy, which is also equal to V. So our potential energy is 1/2 k times delta x squared plus 1/2 m x dot 2 squared.
No,
Yeah.
that's the kinetic energy.
No, it's not.
1/2 mv squared.
Or k.
Okay, and then no x dot. Just regular x2.
Why velocity squared?
Yeah, you're right. X, right. And then, so we can expand delta x, so x1 minus x2 squared plus 1/2 kx squared. And then we can find our Lagrange, which is equal to T minus V, which is equal to 1/2 mx dot 1 squared plus 1/2 mx dot 2 squared. Oh shoot, minus, down here, minus 1/2 k x1 minus x2 squared plus 1/2 k x2 squared. So that's our Lagrange.
Bravo!
Yay! Now I'll pass it off to Henry for the derivatives.
Okay, so to find our equations of motion, first thing we're going to do is just rewrite our Lagrangian, so it's a little bit easier to see for me. So 1/2 mx dot 1 squared plus 1 mx dot 2 squared minus
I have students I don't even know come into my room to get water.
x1 minus x2 squared plus 1/2 k times x2 squared. Okay, this is our Lagrangian, and that's going to be a little bit easier to differentiate. And according to Euler's equation, if we take the partial derivative of the Lagrangian with respect to x, that is going to be equal to the partial derivative of the Lagrangian with respect to x dot, and then the time derivative of this, so ddt. So first, we'll find this term, the partial derivative with respect to x, but because we have x1 and x2, then we're going to have to do this twice, once for x1 and once for x2, so we'll end up with two equations of motion. So if we have the x1 over here, x2 over here, then partial L with respect to x1, we have one x1 term here, one x1 term here. We are going to get x1, and then we are going to want to expand this term, which is going to expand out to 1/2 k times x1 squared minus 2 x1 x2 plus x2 squared. So that's that term, our x1 term expanded out over here. And so the derivative of this is going to be minus 1/2 k times 2x1 minus 2x2. We can simplify this a little bit by canceling out our 1/2 with our 2's. So that's our partial with respect to x1.
Yeah, I'll just tell her that. You guys really enjoy it.
Now with respect to x1 dot, we just have, oh actually, this is actually an x1 dot term, so that should not be in there. So we just have this, sorry, for our partial with respect to x1. So now for x1 dot, we just have this term, which is going to be our mx1 dot. And that's all we have to do for that. And so taking the time derivative of this is going to be d2. We're just going to get mx double dot 1 or ma. And so now plugging this into Euler's equation, if we subtract this over to the other side and get 0 over here, then we get our time derivative with respect to x dot 1, which is going to be mx1 double dot 1 minus this expression here, k times x1 minus x2. And so this is going to be equal 0. This is going to be our equation of motion in the direction.
I would have done x1, y1, x2.
Now, x2 direction, we're going to do the same thing. Partial L with respect to x2. And so we just have, we have two x2 terms here. They're both in the potential energy part of the Lagrangian. And so we've already expanded this out, so we can just take the partial derivative with respect to x2 of this, and that is going to be 1/2 k times negative 2x1 plus 2x2. And then we also have to include this term here. And so taking the derivative is pretty straightforward. We just get plus, right then here, plus k x2. So that's a partial with respect to x2. Now finding the partial with respect to x2 dot is going to be just this term right here. Once again, we only have one term, and so we're going to get mx dot.
Was Van so like maybe the first?
2.
I bet, yeah.
Then finding the time derivative of this,
But yeah, I could
we
go
get
online and get a pair of Nikes. Yeah, like completely custom. I didn't want to. I think you should.
Just like have like the comments of
mx2 double dot. And so then once again, plugging this into our Euler's equation, we are going to get mx2 double dot
so that when you get
minus
past times it blends in.
1/2. Actually, this 1/2 is going to cancel. So we're just going to get k times x2 minus x1 plus kx2. And then that is going to be that equals 0. So those are the equations of motion for a two-spring system.